Thanks for coming, guys. How you doing? Like, dragging yet? I mean, it is 2:30. Hope you got enough caffeine. My name's Garrett Wampole, and I'm gonna talk to you a little bit about a different sort of way. At least I think it's a different sort of way that we have used Spring integration, and that is to as a kind of a back-end processing for an experimental radar system that we're building at MITRE Corporation. So I got the obligatory, you paid for this with your tax dollars, copyright notice. So I'll let that sink in for a second. Well, and while I do, I'll tell you a story. I had these slides done in June, but it took me until about an hour before I was getting on a plane to come down here to get my public affairs officer to sign off on it that I could brief it. So that is how we roll. Your tax dollars at work. A little in the way of introduction. Like I said, my name's Garrett Wampole. Born and raised in Allentown, Pennsylvania, just like the Billy Joel song. Little known fact is that that song's not actually about Allentown, it's about Bethlehem, but Allentown sounded better. Went to school in Rochester, New York. Currently working at a company called MITRE in Bedford, Massachusetts, where I do mostly radars and a very ill-defined domain called battle management. A few of the main systems down there at the bottom, the U2 and Joint STARS, which is a really big one right now. Joint STARS is the Joint Surveillance and Target Attack Radar System. It's off that plane right next to that line there. And in I guess outside of work, my only claim to fame would probably be I had a app come out in the very first batch that went out on the App Store, and that was in 2007. So dating myself a little bit there, I guess. And also, you know, I like the Mets, which actually is a very hard job. Season's almost over, so there is that. And I imagine a lot of you guys aren't familiar with MITRE, so I figured I'd put a few words down here as well. MITRE is a nonprofit company that operates these things called FFRDCs, which are federally funded research and development centers. That's a special type of corporation that the government lets you set up. It's supposed to be, you know, trusted advisor engineering support to the government, as opposed to the for-profit contractors of, you know, the Lockheeds and the Northrop Grummans of the world. So we don't actually build anything. We don't make, you know, fighters or bombs or anything like that. But when the government spends money to buy that kind of stuff, they'll usually bring us in as that, you know, as their engineering support. And, you know, actually it's hard to make those kind of relationships work because, and I can understand it. You know, the Northrop guys see me and they say, oh man, here comes that MITRE guy again. He's gonna, you know, ask us all kinds of questions. But I've kind of taken the approach of the Spring, you know, in the open source community in general. Actually, I find if you give them free code, they'll actually, you know, talk to you a little bit more. And part of what we've done here has accomplished that, really. So we have currently six FFRDCs. The DoD one, which is the one I spend most of my time in, but we have also one for the FAA. We do some work with the IRS. The Homeland Security, the court system, and even the Health and Human Services. God bless those guys. They were dealing with the healthcare.gov thing. I'm sure you've heard of that on the news. Last time I checked, we got approximately 7,000 employees, and 80% of them almost are engineers, which is actually a statistic I'm pretty proud of, because I've worked at places where the ratio of managers to people who actually do work is much higher, and that never seems to work out. We've got two headquarters, Bedford, Massachusetts, which is the one I sit in, and also the Beltway, McLean, Virginia, but, you know, lots of sites, smaller sites around the country and around the world. Got our website there, and a fun little factoid is that it was the MITRE.org was the first name, very first name registered in the .org TLD, and that was way back in 1985. So check it out. I'm ashamed to say it runs off Drupal and not Spring. But we're hiring too, so check it out. We'd be lucky probably to get any of you guys. Oh, and if you have any questions about any of this stuff, I know it's not a typical application area for Spring, but just, we're not gonna stand on ceremony here, just yell out and I'll try to do my best to answer it. So I thought before we got into how Spring integration saved our butt, or actually how we leveraged the Spring technology, might just go a bit, it might be fun to go in a bit about what the radar system is and what it does. And anybody here intimately familiar with the guts of an MTI radar? No? Oh, good, we got one? Oh, good. Excellent. That's cool. Not calling anybody out, I'm actually just checking on my job security. Seems pretty good. So radar, which stands for radio detection and ranging, and it basically consists of something called a transmitter, which sends out pulses of electromagnetic radiation, which propagates through the air until it hits something. That something we have on this diagram is that blue dot there, and it's, I suppose, the simplest possible target you could have. It's called a point scatterer. And what that means is the incident radiation is reflected in all directions equally. Now, in the real world, there's no such thing as a point scatterer. When when the radiation hits a truck or a car or a person or a plane, all kinds of weird things can happen. Some of the radiation gets absorbed, some of it goes off in wacky directions, but the hope is that some of it is reflected back towards the source, which we call a reflection or an echo. And something else that's part of the radar called the receiver can listen for that. And if you know the time at which you sent out the pulse, and you know how fast electromagnetic waves propagate in air, which is, anybody? Speed of light, right? Speed of light. And you know the time that you receive the return, you can figure out how far away that thing is from you. And that's great. But it turns out there's another interesting property of the reflection that you can find out about in the radar. And it just so happens that if that blue dot happens to be moving, if it's moving away from you, the frequency of the radiation that is returned to you will tend to be longer than it was when you transmitted it. And conversely, if the thing is moving towards you, the reflection will have a higher frequency. And that's called the Doppler effect. So when you watch the Weather Channel and they talk about their pulse Doppler radars, that's what they're talking about. They're using pulses of electromagnetic radiation and the Doppler effect to figure out if the rain is coming towards you or moving away from you. And so this diagram is actually, I find very helpful for explaining that, but it's a little misleading, isn't it? Because it's kind of making you think that pulse of radiation is a straight line kind of thing that's just like ping pong balls smashing into each other, and some of them happen to reflect in odd directions. But that's not quite right? Is it? Because electromagnetic radiation is actually waves. So waves, just like if you drop a pebble in a pool, the waves spread out in all directions. That's the same way electromagnetic radiation propagates as well. So I find this diagram is more indicative of that type of thing. So if I've got a moving target out there represented by the smiley face dude, and I'm able to detect his reflection from my transmitted radiation, what can I really say? The only thing I can really say is that he exists somewhere on that circle. I'm not exactly sure where, because all I can really tell is that I got a reflection and the Doppler is some value. But what I really want to know, what I really am interested in surveillance, is exactly where that target exists on that circle there. Now, in real life, I might use a certain type of antenna or a waveguide to restrict the area in which the waves, propagate. But even so, that circle arc there might be 5, 10, 20, even 100 miles in length. And I'm not so much interested in the guy somewhere in this 100-mile area. I want to know exactly where he is, the spot on the ground. And it turns out that's a really difficult problem. Lots of people have made their living trying to solve that. One way to do it is to use multiple monostatic systems. So I forgot to tell you that last thing is called a monostatic radar, which means that the transmitter and the receiver are in the same location, basically. If I use multiple monostatic radars, some people call that multistatic, which are, just what it sounds like, 2 single monostatic radars that are in different locations. Now, I can narrow down the possible points at which the target could be to basically the intersection of those circles. If I detect that same smiley face guy on 2 of those circles, I can say, because we haven't yet figured out how to have matter exist in 2 different places at the same time, he has to be at the intersection of one of those points, at one of those green dots. And that's a lot more information than I had before, right? Those dots are actual points on the ground, and that gives me a precise location of that target. And so this all sounds great, but it turns out that there are a host of IT challenges that crop up when you try to actually build a system that does this. And they're thorny, and in fact, they're so thorny that people almost have scrapped this type of design in favor of something called a phased array. And what a phased array basically is are tiny monostatic radars, modules they call them, transmitter and receiver modules, that you put right next to each other. They're inches away. They're all in a single package. And just like any engineering choice, there's trade-offs. There's trade-offs between a multistatic design and a phased array. For example, the multistatic systems, you need to actually have a place to put each of your 1 or 2 or 3 or 4 or 5, however many you have, sensor elements, which can complicate, deployment. But, in phased array, everything's in one box. However, the multistatic systems are much simpler because they don't have to have all the complicated power setup and electronics for multiple transmitter and receiver modules. So, for example, the ones that we build in our lab of the multistatic type are probably about this big, and they weigh 10, 15 pounds. You can carry them under your arm, whereas the smallest phased array I've ever seen weighs 600 pounds, is about the size of this lectern, and needs a kilowatt of electricity to even turn the thing on. So, so there's a trade-off. So as you can imagine, the individual multistatic elements are cheaper to build. In phased arrays, it's almost a joke in the radar community that if you even say new radar, it costs $1 billion right off the top. And it's not uncommon to spend $2 billion, $3 billion developing really good phased array radar. But I say the plus there on the potential for greater accuracy, I say that because having control over all those little modules lets you do things like purposefully use one of them to cancel out the signal in one part and reinforce it in another. They call that beam steering or electronic scanning, and it lets me kind of detect at a greater accuracy. But again, you've got the software that you have to write to process that kind of data. The setup for that is very, very complicated. So, multi-static sounds like a good option, right? But there's that last minus there. The coordinated central processing is a big one. And it turns out that I want to highlight that guy as soon as I can actually click on PowerPoint, because that is a place where we have used Spring integration to good effect, and I'll tell you about that. But first, I want to, I keep saying, we're processing the radar data, and that's how we're using Spring integration. But I'll give you a few clues as to what that data looks like. So you remember we talked about the two types of data that come off the system, which is really how far away the target is, and the Doppler effect, the speed, how fast is he moving away from you or towards you. And what will happen is, systems will generally quantize their maximum ranges in speed and in range, so that maybe we call them bins. So one bin in range might be half a meter or a meter or 2 meters. And conversely, in Doppler, a bin of Doppler might be a half a meter per second or 1 meter per second. And you end up with sort of this 2D matrix where the cell value is some indication of the type of signal that you received at that range, at that speed. It's usually expressed as a ratio, a signal-to-noise ratio. A high signal-noise ratio means it's very likely that there's a target at the speed and that range, whereas a low signal-noise ratio is, probably no target. And the sensors will generally integrate these measurements over some period of time, which is called a coherent processing interval, or a CPI, and they'll cut it off. That's, depends on what you're trying to track as to how long a CPI might be. And they'll cut that off and say, here's a bunch of data, and they call that a range Doppler map. And these things continuously come in from the sensor once each CPI. And it's a ton of data. And what we're really trying to do is, over time, reduce that thing down to just and report the targets that are moving within the sensor's field of view. So it's certainly a data reduction problem. And what you do with those reports is generally put them up on a map for people to look at, so they can see what things are moving in their area of interest. And so we've got this, but the extra wrench in the mix here with a multi-static setup is that these sensors, they don't know about each other. They can't talk directly to each other. So they need to somehow send this large stream of data back to that central processing hub, and that thing's got to figure out, if the data comes in out of order, or it might be not as timely, match the things up, do some processing, and report on the targets. And that's generally set up as a pipeline, a processing pipeline. So just like that command line pretty much reduces the amount of data from an HTTP GET to lines that only have a certain piece of text in it, to the number of lines. We're trying to do the same thing with that radar data. Get it in, make sure we coordinate the timing right, process it so that we can find out where the targets are, track them over time, and then figure out where on Earth that is, and send out reports to someone who's interested in them. And so back to those list of challenges I was talking about that crop up when you try to build multi-static sensors. Here they are. And so, like I was telling you, matching up data from those sensors that may arrive at different times, or they may arrive out of order. Coordinating those pipeline steps that are sometimes are stateful, and they may depend upon data from the other sensor needing to be processed to a certain point in the pipeline before I can answer the question for sensor 1. That's a big one. And then, of course, keeping up with near real-time processing is also very key, because it doesn't do you much good to find out that something's moving 10 minutes ago. I want to know about it right now. So those three are very software engineering centric and have to do with how the software is set up. The next two are more deployment oriented, and really supporting the multiple types of deployment was key for us, because in keeping with the benefit of a multistatic system, that each sensor element is lightweight and it's easy to set up, you don't want to have to build a data center next to it and say, well, you need all this processing power in the back end to process the thing. So whether it's a bunch of laptops sitting next to the sensor, or maybe you have a server that you want to process all the data at, or maybe you want to process it to some point and then ship the stuff across the country to be processed at another location. All of those deployments are things that we've tried out in our experimentation. We want to have the software be able to support that, and Spring integration really helped us out there. And then similarly, the different types of input and output are also very important. Depending on how you set up the system in the beginning, the sensor may be hardwired into your processing, or it may have to transmit to you over a wireless network. And subsequently, on the other end, you may want the mover reports to come out as KML that you can look at on Google Earth, or maybe you want a stream of STANAG 4607 data to go out on the network, or perhaps be saved to a file. Probably not familiar with STANAG 4607. That's a NATO standardization agreement, that's what STANAG stands for, on how radar data is represented. It's a binary, word-oriented protocol from the 80s. It's terrible. But anyway, and so we don't want to have those assumptions on how the sensors give us data or how we want to provide reports baked into the system. And the last two are more process and development sort of challenges that we've kind of agreed upon over time, just from our experience developing systems, that to work out bugs or test out new algorithms, the development environment, recreating, these sensors never really know what they're going to look like until you actually deploy them against real targets. And once you have that sort of test case, it's traditionally very difficult to recreate it in a lab setting, so that you can do unit testing, you can do repeatable development cases to really validate the things that you're doing. So we wanted to solve that problem. And then, of course, and this has always been an issue in the systems that we've seen. You send in some input, you get some answer, and you have no idea what happened in the middle. So we really wanted to be able to reach into the system and see what was going on in those intermediate processing steps in that pipeline, and save them out for later, so that the math geeks could go back and look at them. And just the concept of wiretaps in Spring integration, and the fact that you can use the message channel to sort of control the threading model, was absolutely the perfect solution for that problem. So the rest of this briefing really is some slides on how Spring integration really helped us tackle a lot of these challenges. But first, first thing first, those steps in the processing pipeline are basically Spring integration service activators, which call into this thing called the MATLAB compiler runtime. MATLAB, you guys may have heard of MATLAB. It's a matrix laboratory product by a company named MathWorks, also Massachusetts-based. And it's really a math geek programming language that the guys like to use to develop algorithms to process sensor data. And we wanted to allow them to work inside that comfortable environment, MATLAB, but then when we went to deploy the thing, not have to sit around and recode all of their algorithms in C++ or Java or some other language. And then now we've got this extra step of verification and validation that our target code matched their MATLAB compiler, their MATLAB code. So the service activator that we developed actually calls into a MATLAB object managed by that compiler runtime thing using an API that we've developed. And I'll tell you the one bummer about that is that this MCR is really single-threaded. Once MATLAB is running a function, once one of those service activators gets called, if another thread, say processing data from the other sensor, tries to call into MATLAB, it will be blocked until the first one returns. And that's an artifact of the way MATLAB sets up this compiler runtime thing. And we've worked with them quite a bit on trying to come up with solutions, but they have something called the parallel toolbox that they'll sell you that's basically a computing server that manages a bunch of those MCRs, which are more or less headless versions of MATLAB without the graphical user interface. But it turns out that you have to marshal the requests to that compute server in a format that looks to me, just from wire sharking it, looks to me like RMI, and that would be fine for most applications, but these things, at least in our processing chain, are sub-second operations, and just the fact that marshaling the requests and then deserializing the result from that takes so much time that it negates any benefit you get from the parallelism. So if you guys could solve that, that would be wonderful. But Spring integration actually, just using the Spring framework in general, we kind of used that to work around this, and I'll go into that later. On the multiple input-output types, clearly the channel adapter abstraction is the way to go, and it's key in these types of applications, sensor processing pipelines, because all you want to do is change the edges, the way data comes in and the way the results get reported. And I can't tell you how many radars I've worked on where when we ask the question to, hey, can you change it from reading data off TCP to a UDP stream? And that costs millions of dollars because I got to rewrite all their software. Here, as you can see, we've written a bunch of channel adapters that don't make any assumptions about what happens to the data after it gets off the pole or reads it off that channel adapter. And in fact, that last one, we've actually done a few experiments on processing some amount of data for a couple of minutes, and then we go back and process it in reverse time to sort of see the tracks moving in the opposite direction. And it just, in the way the math works out, you can stitch those guys together and get longer tracks of the target if you do it in reverse time. And doing that was very easy because the rest of the system doesn't know that you're playing the data backwards. All I got to do is flip the switch to use a different channel adapter, and it takes care of rewriting the data that it reads in from forward time to reverse time. So that was really cool. In the development environment space, so this is where we're talking about recreating what happened, in a given deployment in near real-time sensor processing. It's always a challenge, but you need to do it to debug issues that crop up, and also when you develop new types of processing algorithms. Test it against a representative data set in terms of how that data appeared in near real time in a real operation. And again, so basically add a feature onto the channel adapter that says, well, now I want you to run in real-time mode, which basically means I look at the timestamps on the data that I'm reading off whatever the source is that's coming in. And when the polar, the spring integration polar, goes to read from that channel, he will be blocked for some certain amount of time that corresponds with the time it took for the sensor to actually produce that data. And if you just run a bunch of these things in separate threads, you get pretty much a recreation of near real-time data as it looked like when the system actually produced it in the field. So on the flexible deployments front, this was really huge. Not only to allow us to benefit from the small footprint of our multi-static sensors and deploy the processing in different ways, but also to get around that single-threaded MATLAB compiler runtime thing, because all I need to do is start up multiple JVMs, each with a Spring context, running a certain Spring integration processing flow that corresponds to the type of deployment I want to do, be it one big server or 4 laptops, or send the data across a long haul network back to a central processing location. And it's truly as simple as using a different Spring integration context configuration. And you guys may laugh that we're still using XML, Spring configurations, but it was the perfect unit for us to deploy the different types of the system. So you start up the radar and it just says, hey, are you running in all at once big server mode, or are you running in 3 laptops mode? Here's the context you need to fire up for that given deployment, and they're all pre-configured to work right. So for example, so here's a couple of our Spring integration flows, data flows. So we got this running on one laptop, taking in data from two sets of two of those multi-static sensors. And you see those 2 channels at the bottom. There's a router that says, well, this is data from sensor 1. I want it to go to this laptop. If this is data from sensor 2, I want to go to the other laptop, which have their own JVMs, their own MATLAB runtimes, so they can run in, obviously, parallel from the other one. So there'll be 2 of these processing data from one of each of those sensors through the coordination step of finding out, matching it up in time with data from the other sensor. So here we create the target tracks in geolocation, and then create the products. In this case, it's KML, and send it out to Google Earth for visualization. So that would be one deployment. Another one might be, hey, do the whole thing at once. So my algorithm developers back at the office, they run this flow because they're interested in looking at the system performance across the whole processing pipeline. All I have to do is give them another Spring context file for them to run this, and really, to send it out to the field, it's chopping this thing up into separate XML files and just running it on different PCs. No recompilation needed, which is huge in the sensor world. So I mentioned the coordination, the processing coordination issue, which is really one step may keep some state, and it may need to remember what happened possibly from processing data from another sensor before it can continue on to process the data that it's working on. And especially when you start getting into multiple JVMs, definitely a concurrency issue there. So what we've done is really you just decorate one of those service activator components with what is essentially a network-enabled cyclic barrier. So we define phases, which correspond to a given processing step for a given sensor. So the number of processing steps times the number of sensors equals the number of phases that are defined for a given setup. When you're ready to go, you call arrive at phase, pass in the one that you're working on. When you're done, you say, hey, I need to now wait until phase 1. So phase 1 corresponds to processing step 0 for sensor 1. If this contacts the phase server who says, hey, the other guy hasn't said that he has arrived at phase 1 yet. So you sit around and wait, basically block, until I get an announcement from the other processing who's on a separate JVM that he has arrived at phase 1. He's done processing the prerequisites for that. And once that occurs, the server sends out another packet saying, hey, we're all at phase 1. Now you guys can move on. And that's something you guys probably all recognize from the Java concurrency package. But really the difference here is that it's just something you add on to one of those service activators, and it's network enabled. And the big problem keeping up with real time solution, the message channel abstraction really is tailor-made for that. And so really, especially given the chance to provide an implementation of that message channel, which in our case sorts the data that's buffered inside that channel according to when the sensor produced it. And this smooths out cases where data comes in out of order or it's excessively latent. And I say fixed size there, but we're actually working on a mechanism that, using a separate network protocol that sort of sits on top of UDP, it's called UDT, the UDP data transfer protocol. And it's got a pluggable congestion control type of mechanisms and produces all these statistics on what the network is doing. And so what we're experimenting on is taking those congestion control statistics and putting them in as headers inside the Spring message. And then when it gets in-queued in one of these message channels, it can look at what type of congestion you're experiencing and dynamically size the buffer of these channels in order to kind of optimize how much buffer space we need according to what type of network environment you're experiencing. And so just by way of proving that this stuff actually works, we've done, just this last year, we did an experiment with the Department of Homeland Security. It turns out that smugglers, especially on the northern border of the United States, they like to get in their ultralights or their small Cessna planes and fly very low, close to the ground in river valleys or where it's hilly or there's mountains, in an attempt to avoid detection by the typical FAA air surveillance radars that are all over the country. And DHS has noticed this, and so they brought us in to try and use the benefits, like we were talking about, of a multi-static system where it's easy to deploy. The sensors are very small. You can just stick them on top of those hills and try and detect these smugglers that are flying into the country. And frankly, we have found those dudes. And And I bet you never thought that Spring integration would be used to capture drug smugglers, but it has happened. And so, yeah, give yourself a pat on the back for that. And so, just kind of some parting thoughts on that first bullet. I've had to fight this battle a number of times with my engineering leadership at MITRE and also with our customers. It seems that as soon as you say enterprise service bus, people think slow. And I don't know, I'm not sure where that comes from. Maybe it's just the traditional application areas of business to business and that kind of thing. But it's not true. This stuff works in near real time. And Spring integration is lightweight, and that's great because it enables performance, and it's also great because it doesn't really force you into too many paradigms, which I think is proved out by the fact that you can use this thing to process orders from Twitter or a mobile app, and you can use it to process radar data. And just the fact that you have that thing underneath, the Spring framework, the IOC container, and all of the JMX management stuff that's baked in there, all of the bean injection, that stuff is just gravy. And I can't tell you how many times we're able to make quick adjustments to the system that we set up for DHS by just running a few spell expressions to change how the algorithms were working. Let the thing run for a few minutes, see how it's working. Say, hey, yeah, that looks good, and then I just update the context configuration file to make it permanent, which was really rapid response, and our customers were very, very happy with that. And so, and lastly, hey, thanks for the community. I mean, that it was not a traditional application, but I work with some of the people on the forums on how this stuff comes together, and it was very a joy really to program in this environment. So thanks a lot for that. And so that's really all I got. If you guys have any questions at all, I can try to answer them to the best of my ability. Yeah. Oh, so the question was, how do we deal with errors in the data over unreliable networks, which is something that happens all the time, especially when you're trying to get data off the sensors over a wireless network in a mountainous region like the one we were doing for DHS. And more or less, the answer is you throw it out because with resends or trying to do forward error correction or something like that, it just takes too much time. It's more important that we process the next piece of data than fix the error from the last piece of data. So and that is just for timeliness and to try and make sure that the movers that we're reporting are as close to real time as possible. Is pretty much the deal there. Yeah. Yeah, good call. So the question is for the algorithm developers who are working in MATLAB, can they run some of the Spring integration things in their development environment to sort of test it and make sure it'll work in the deployed system, basically? And yes, the answer is yes. So what we'll do is, I'm sure if you're familiar with MATLAB, MATLAB has the capability when you start MATLAB, it actually starts a JVM under the hood. And so you can create Java objects and call methods on them. And what we'll do is pretty much take the service activators, take the channel adapters that we use running in Spring integration, and just say to the MATLAB guys, hey, here's how you create a channel adapter to read data from a file, or here's how you create one to read it off of a network socket. And they can do that just within MATLAB, not running a Spring context, not running the whole deal, but use the components that will be eventually called by Spring integration. And so that does give us a little bit more confidence that when they see some behavior in their development environment, it will be pretty much the same thing in Spring integration. Good question. Good question. Yeah.
So were there like multiple deployments running at the same time? So you mentioned about laptop deployments and kind of server, right? So was it possible to have data coming to laptops as well as server at the same time, or it was kind of one at a time?
Sure. So the question was, do we support all the multiple deployments that our context support? Can you run several of them at once? And sure, it just depends on the number of JVMs you're willing to start up. I'll tell you for the DHS experiment that we're doing, we're processing, I'll say 50% of the pipeline on a laptop that's sitting right next to the computer, right next to the sensor in a weatherproof shelter, obviously, because it snows a lot where we are. And it's hooked up to basically a terrestrial network that sends the data all the way back to our facility in Bedford, where we process the rest of it. And then we have a special network that sets up, that sends the products, the actual reports of the targets, to our customer, basically, so they can look at it. So that's like basically three different versions of different Spring integration contexts that are running in that case. Does that answer your question? Yeah. That's a good question. So when I say, the question was, when I say near real time, what counts as near real time? And I'll tell you, it's for the time I get some data off the sensor to the time I'm expected to produce a report, a track report. It's in the 2 seconds or less type of regime. And that involves getting data off of however many sensors I have set up in my multi-static environment, getting the data from all of them, making sure it matches all up, running the processing pipeline, and converting and reporting that to something that I can show on a screen. So not a huge error budget. That's why it doesn't behoove us to, if there's problems, to try and go back and fix them. You just, hey, that packet was screwed up. I'm just going to drop it on the floor and wait for the next one. Yeah. So the question was basically, how am I running Spring integration? Is the Spring integration a server and a bunch of people are accessing it, or otherwise? And I would say otherwise. In that case, with the laptops, each one of those laptops is running a separate JVM with its own Spring integration context that is running a integration flow according to how the context is set up. And depending on what our IT setup looks like, we may do a third of the processing on each one of those laptops, or maybe we'll do 10% on one and 80% on a server, or maybe we'll do 10% on a laptop and 80% on our server back in Bedford. And that all depends on, so there's not really a server-client relationship unless you want to call, the step number 2, the server who receives the output from step number 1. But they're really peers in a network of Spring integration contexts that are processing a bunch of data, really. So yeah, it's not, I wouldn't call it a server client. Does that kind of answer your question? Yep, sure. Back. So the question was, before we tried Spring integration, what were the issues we ran into? Is that? Oh, okay, yes. That's also a good question. So did we try anything before we tried Spring integration? And yes, we tried a product called Mule, which is another type of ESB sort of concept. And the reason we eventually settled on Spring integration, I would say, is because of that lightweight paradigm that I talked about on the last slide. It seemed like Mule and Mule is great for the application space that it is good at. But when we tried to make it work at near real-time speeds and in the different types of deployment scenarios we had, we just found that it just sort of backed us into too many corners. So after kind of flailing with that for a bit, I stumbled across Spring integration almost, and just noticed that the framework itself buys you all that management capability and injection and all that great stuff. And it just seemed that integration was a very thin layer on top of that just let us do what we wanted to do in terms of a sensor processing pipeline. Good question. Yeah. Oh, and that has happened. So yeah, the question is how do we manage the software on those given the different types of deployments? And I won't lie to you, we have made people climb up the side of that mountain in the dead of winter to reboot the server. And yeah, when the thing, but if it's hardware related, if it's power related, there's not much you can do besides get up there and flip the switch. But in terms of configuring the software itself, being able to just put a managed resource annotation on top of one of my algorithm classes and have it automatically notice all the configuration parameters that are in there, and I can just go in with JMX and tweak them and have it take effect live. Is a big deal. Is a big deal in terms of being able to react to the different changing conditions, even weather-wise and different types of targets, very very quickly. So that was a good win. Anything else? Well, hey, thanks a lot, guys. Appreciate you stopping by.